We are now going to apply the Poincare-Benedictson theorem to a well-known equation called the van der Pol equation. This is actually a second-order equation, so we'll first need to convert it to a system by letting dx dt equal y, in which case the second derivative with respect to t of x is actually just dy dt, and dx dt is y. And then if we solve for dy dt, we get that dy dt equals minus x plus 1 minus x squared times y. Now I claim that this system has a periodic solution like the one that you see below, but I think we should first look at it in slopes to see that that's the case. So here we have the phase plane for the van der Pol system. And then if you'll notice, if I click on a solution, you'll see that the solution spirals outward towards what I think is a periodic solution. I'm going to increase time here to see that the x and y of t both are periodic. Okay, if I pick on a solution that's outside of that periodic orbit, you'll see that, again, it spirals inward to the periodic orbit. So let's see, using the theorem, why we know that this periodic solution exists. So in order to apply the Poincare-Benedictson theorem, I need to find a region of the phase plane where if a solution enters that region, then it will remain within that region for all time. So what I'm going to do is first notice that 0, 0 is an equilibrium point. And so I cannot include 0, 0 in that region. So I'm going to draw a circle of radius 1, and I'm going to say that my region is going to lie outside of that circle of radius 1. And then I'm going to draw a funny looking region which will enclose my periodic solution. So I'm going to start at y equals 3 and then move across. Then I'm going to come down x equals 3. Then I'm going to connect x equals 3 to y equals minus 3. Then I'm going to come along y equals minus 3. And I'm going to go up x equals minus 3. And then I'm going to connect that to y equals 3. And I claim that if a solution enters that region, then for some time it will remain in that region for all time. So in order to see this, I first need to see that the solution is going to remain outside of that circle of radius 1. So I would like to see what happens near the circle of radius 1. In order to do that, I'm going to look at the system in polar coordinates. What is r dr dt? Well, that's x times dx dt plus y times dy dt. So that's going to give me x times y, and then minus x times y plus 1 minus x squared times y squared. You'll see that x times y and minus x times y cancel. So I'm left with that dr dt is equal to 1 over r times 1 minus x squared times y squared. Now, when r is equal 1, I'm going to claim that that is positive. And we can see that because the y squared is positive, the 1 over r is equal to 1, and 1 minus x squared is also positive. And that's because x squared plus y squared in this case is equal to 1. And so that means that solutions that are near r equals 1 are going to be pushed back outward. And so they're going to remain outside of r equals 1 because the derivative with respect to r with the radius is positive. And that'll push solutions outward into our region R. It's a little more complicated to see that solutions are going to remain inside this region R, but in fact, if solutions wander into this region R, you'll see that they will remain inside that region R. They'll go towards some periodic solution that looks like that. And so by the Poincare-Benedictson theorem, this van der Pol oscillator has a periodic solution at like the one that you see displayed there.